In this video, we are going to be looking at the chemical properties of specifically triacylglycerols and at some reactivity that have to do with these type of fatty acids. So when it comes to the chemical properties of triacylglycerols, understand that here we're going to be looking at chemical reactions that can be done with these molecules. The first example that we have in this slide is the hydrogenation process that can happen to certain oils in order to make products like margarine or shortening. So the hydrogenation reaction, it is something that we explored previously. Remember that in the reaction of hydrogenation, we have an alkene reacting with molecular hydrogen in the presence of a catalyst. Here I'm going to have platinum. It could be nickel, it could be palladium. And we're going to form an alkane. Now, understand that in commercial hydrogenation, we're going to be adding hydrogen, okay? And we are going to do partial hydrogenation. So not every single molecule in our oil is going to be converted into a saturated triacylglycerol, okay? Now, understand that when partial hydrogenation occurs, then that gives rise to the creation of a soft semi-solid fat. That's why we have products like shortening or margarine, okay, resulting from this reaction. The reason why this is used is because you have a more saturated product that has a higher melting point. Now, one of the things that I should specify is that when this reaction first was initiated and was utilized, one of the problems that was created is that the hydrogenation reaction created trans fats. Okay? And remember, those trans fats is when you have now the groups within the carbon-carbon double bond be on opposite sides of each other. So maybe some of you have heard that trans fats are not good for you. And the reason why they're not good for us is because we don't have the enzymes to actually process them. So what happens is that they tend to be accumulated in the body, and they at times are going to be triggering the production of some other molecules that are not good, like increasing our levels of cholesterol. Now, understand that if you buy margarine or even shortening in the market right now, they actually precisely say no trans fat, because in industry they have done extra purification steps to remove the trans fats that result from the hydrogenation reaction of oils. Another reaction that can occur with triacylglycerols is going to be hydrolysis. And as you remember, hydrolysis is going to be, we have two types of hydrolysis. We have acid hydrolysis and we have base hydrolysis. And we're going to talk about both of them. In acid hydrolysis, which is the one that we have in this slide, we are going to be converting our triglyceride into its components, glycerol, and in this case, because of the original molecule, we're going to have palmitic acid. Remember, this is not chemistry that is new. Remember that in this molecule, we have ester bonds, and we learned in chapter 14 that if you have an ester that undergoes acid hydrolysis, because we're reacting with water or acid, or we have an enzyme, and we're going to be studying enzymes in the next chapter. But understand that enzymes are going to be molecules that can be used as a catalyst. So if we take an ester in acid hydrolysis, we're going to be obtaining an alcohol and a carboxylic acid. And as you can see, the product of the acid hydrolysis of a triglycerol gives you exactly that. The glycerol, which is going to be the alcohol portion, and you're going to have 3 fatty acids, because remember, triacylglycerols have 3 components of fatty acids. So this is going to be your carboxylic acid component in the molecule. As I mentioned in the previous slide, and we have learned previously, when it comes to the reactions of esters, we can also hydrolyze esters in the presence of base, okay? And when that occurred, we already learned that that is called saponification. What does this mean in triacylglycerols? That we are going to be taking our fat or oil, we're going to be reacting it with sodium hydroxide or potassium hydroxide, and we're going to be heating it. Remember, when we had this before, our ester, and I'm just going to highlight the ester motif, is going to be hydrolyzed to an alcohol and a carboxylate salt. Here, our alcohol is going to be glycerol, and our carboxylate salt is going to be the carboxylate from the fatty acid. Understand that these carboxylate salts that come from triacylglycerols are what we call soap, because these molecules can be utilized as soaps. So, when it comes to comparing organic and lipid reactions, as you can see in table 15.3 in your textbook, it is summarized what are going to be the organic reactions and what are the relation to the lipid reactions. We have esterification, hydrogenation, hydrolysis, and saponification. Remember that hydrolysis refers to acid hydrolysis specifically. So, as you can see, we learned these organic reactions previously. Esterification came from chapter 14. Hydrogenation came from chapter 11. Hydrolysis came from chapter 14. And saponification came from chapter 14. And in the last column of this figure or this table, we can see specifically how this is related to the lipid reactions that I just discussed in detail. We are now going to be moving on to the next member of the family of fatty acids when it comes to lipids, and these are called phospholipids. And times they are also considered glycerolphospholipid, okay? And later we're going to see out of the sphingolipid how sphingomyelin is part of that, okay? Now, when it comes to phospholipids, as you can see, they contain glycerol, they contain 2 fatty acid molecules, and they have a brand new functional group that we haven't seen before. So, phospholipids are going to have in the last OH group of the glycerol, that is going to be bonded to a phosphate group, and that phosphate group is going to be bonded to an amino alcohol. We are going to be looking at all of these components one by one. We already know what glycerol looks like. We already know what fatty acid looks like. So the first one that we are going to be exploring is the amino alcohols. So when it comes to the amino alcohols, just like the name says, these molecules are going to have an amine group. So the amino comes from having an amine component. In the alcohol comes from having a carbon atom bonded to a hydroxyl group. So here we have 3 different examples of amino alcohols that have been found in nature, and they include choline, serine, and ethanolamine. Understand that each one of these molecules, they are ionized at physiological pH, which means that the pH is 7.4. The reason is that around that pH, this molecule is going to be having, specifically for depending on the component of the molecule, is going to have a charge. So ionized means that these molecules, I'm just going to highlight them in green, are going to have a charge. So let's look first at glycerolphospholipids. As I mentioned before, glycerolphospholipids contain glycerol, which is bonded to 2 fatty acids. Then the last OH of the glycerol now is going to find a phosphate group, okay? And that phosphate group is going to be bonded to an amino alcohol. So understand that the 2 fatty acids that we have in the molecule are going to form ester bonds. So these bonds right here are going to be ester bonds. Okay? Now, a hydroxyl group that forms an ester here in the bottom one, I'm just going to highlight it with a different green. So that one specifically is going to have a particular name. That is going to be called a phosphoester bond. And the reason is because now the ester bond is between a phosphorus atom and an oxygen atom, okay? And then that is going to be linked to the amino alcohol, specifically through the OH in the amino alcohol, okay? So if I highlight this bond is with OH group in the amino alcohol. Let's look at these molecules more closely. So here we have a molecule of a glycerolphospholipid, okay? So if I highlight the different components, you can see here, okay? And if I number the carbons in my glycerol molecule, this is carbon 1, carbon 2, carbon 3. I have on carbon 1 and carbon 2 ester bonds to the fatty acids. Carbon 3 in the glycerol is going to be bonded to the phosphate group, making that phosphoester bond, and that is going to be bonded to the amino alcohol motif. Now, understand that when it comes to glycerophospholipids, because your amino alcohol is ionized, it is known to have that charge present. So glycerophospholipids have what is called a polar head, and it has nonpolar tails. The polar head, okay, is going to be containing the ionized amino alcohol, okay, and the phosphate portion. And remember, if it's polar, it can be attracted to water, okay? Then, because of the nonpolar hydrocarbon tail, okay, That is going to be the nonpolar portion of our glycerolphospholipid. Now let's mention the last member of the fatty acid family, which is going to be sphingolipids. Here we have one example of a sphingolipid. Which is going to be specifically sphingomyelin, okay? Now, let's understand something. When it comes to sphingolipids, they are not going to have glycerol as their backbone. I am now going to be highlighting, okay, the backbone of a sphingolipid, which is this molecule that I highlighted in blue, and that is called a sphingosine. Okay? We are going to have only one fatty acid, okay? And this fatty acid specifically is going to be bonded through an amide bond. And then similar to what we saw in the glycerolphospholipids, we're going to have a phosphoester bond. And we're going to have an amino alcohol. Now, specifically understand that in sphingomyelin, we're going to have the amine group of the sphingosine form that amide bond to the fatty acid, okay? The hydroxyl groups present in here are going to be specifically the last one. If I highlight it, it will be right here. This arrow that I put there is going to be forming a phosphoester bond to the amino alcohol. And depending on what it is, as you can see, we can have choline or we can have ethanolamine. Now, why are sphingolipids important? Because, for example, sphingomyelin is going to be abundant in the white matter of the myelin sheath, which is the coating of the nerve cells. And specifically, having this biomolecule surrounding nerve cells is going to be increasing the speed of nerve impulses, and it also insulates and protects the nerve cells.